KURINJI Senior Secondary School, CBSE, Namakkal.
Successful result producing school in state every year.
Administered by the Board of Directors with over 35 years of experience in the teaching field.
Special attention on art, craft, music, dance, silambam, yoga, skating and karate.
Focus on Hindi Sabha and Spell Bee Olympiad exams.
Smart class for effective and innovative learning and well-furnished library.
Solitary importance on sports and games in state and national level.
WhatsApp facilities to know activities of students and school inside the campus.
NEET, JEE, IIT coaching experts from Rajasthan and Andhra Pradesh along with our effective teachers.
Admission registration for classes LKG to +2.
KURINJI Educational Institution, Kavetipatti, Namakkal. Admission in progress. CBSE, KG to 12, contact 9025895176. Metric 6 to 12, contact 9344567484. For online admission, log on to www.kurinjischoolnkl.in.
In continuation to the last class, in this class we are going to discuss about thermal expansion. In our previous class, when we were in a discussion about measurement of temperature, there I told you the working principle of thermometer is matter expands on heating. That is the basic principle which helps us to design a thermometer. Thermometer helps us while measuring the temperature or to measure the temperature. So from that information, what is our conclusion? Matter expands on heating. So it is not only a fluid, solids also, right? So solids, liquids, gases, all will expand when you are going to provide certain amount of temperature to that particular matter. Okay, right. See, for example, some sealed bottles, that's what you can see. Some sealed bottles with metallic lids are so tight screwed, so that one has to put lid on the hot water, lid in the hot water, so that it is easy to open the lid. That's what our daily life experience, right? See what is happening here exactly. When you put that lid, which is fixed tightly to the bottle in hot water, that lid, that is what metal cap or metal lid, receives certain amount of heat energy from the water so that it expands. When it is going to expand, automatically it will become like that is what it will become somewhat loose, so you can easily remove that lid from the bottle. That is what the general life, daily life experience. Okay ma? Right. Now similarly, see in case of liquids, that's what I already told you, that is what in case of thermometer, mercury is going to expand. Not only mercury, see most of the liquids are going to increase, most of the liquids are going to expand when they absorb certain amount of heat energy, so they will expand. But there is some difference when compared to these many liquids to the water. That is what the special behavior of water, which is called as anomalous expansion of water, that we will discuss in the same class. After 10 minutes we will go to discuss what is the anomalous expansion of water, right? So come back to our discussion. Here not only solid, that is what lid cap made up of metal, lid cap of the bottle. Next, not only liquid, that is what mercury or any other, whatever it may be, that is what water, like that. And if we take gas also, right? So in the case of gases, a balloon partially inflated in a cool room may expand to full size when placed in warm water. This is generally the children are playing with the help of balloon, like that there itself. On the other hand, a fully inflated balloon when immersed in cold water would start shrinking due to the contraction of the air inside. So these are all what, whether it may be a lid made up of metal, whether it may be mercury which is present in the thermometer, whether it may be that is what balloon made up of, that is balloon contains certain amount of gas, whatever it may be among these examples, what is happening, what is happening parallelly? Matter expands on heating. Matter expands on heating. Okay, right. Ipo, see here. Now, it is our common experience that most substances expand on heating and contract on cooling. A change in the temperature of a body causes change in its dimensions. A change in the temperature of a body causes change in its dimensions. The increase in the dimensions of a body due to the increase in its temperature is called thermal expansion. The increase in the dimensions of a body due to the increase in its temperature is called thermal expansion. Is called thermal expansion, right? The expansion in length is called linear expansion. The expansion in area is called areal expansion. The expansion in volume is called volume expansion, right? In this class, or initially regarding this topic thermal expansion, initially we are going to discuss about a solid, a matter which is a solid we are going to discuss, right? After completion of this we will go for liquids, then we will go for gases, right? Now we are going to consider a solid material and we are going to discuss thermal expansion of a solid matter, right? See, the solid is available, that is available in case of rod, plate and cube, okay? Rod, plate and cube. Dimensions will be different now, because rod means only area, rod means only length, okay? Plate means area, cube means volume. So plate means length into breadth, cube means length into breadth into height, okay? See, for example, the lunch plate, what you are taking, there itself we have to talk about the area. Suppose if we take a metallic rod, that's what we are using in case of building construction or some other our daily life purpose. It has only length, right? It has area of cross section, that is what pi r square, it will be different. But mostly we used to talk length. Suppose if you are going to, that is what Rubik cube, right? Otherwise cubic like material, whatever it may be, whether it is made up of iron, aluminium, copper, silver, gold, whatever it may be, right? Because it should be a solid material, that's all. It should be a solid material and mostly made up of, that is what generally either lead or glass, gold, silver. Generally we used to come across iron and aluminium, okay? A silver also. Okay. See, if you are going to see thermal expansion in case of rod, what will happen? See this. If the substance is in the form of a long rod, then for small change in temperature, delta T, the fractional change in length, delta L by L, is directly proportional to delta T. This is what practical observation. What we can observe. That is, what is the practical observation? Delta L by L is directly proportional to delta T in case of thermal expansion of a solid material. Okay, what is delta L? Change in length. What is L? Initial length. What is alpha? Coefficient of linear expansion. What is delta T? Change in temperature. Okay. If the substance is in the form of a long rod, then for small change in temperature delta T, the fractional change in length, delta L by L is directly proportional to delta T. So that what can we write? Delta L by L is directly proportional to delta T means, if you are going to remove the symbol directly proportional, if you want to keep is equal to, then delta L by L is equal to alpha 1 into delta T. Right? Okay. It is in case of rod where we are going to talk about only the length. Suppose if you take plate which has area, then delta A by A is equal to 2 into alpha 1 into delta T. Suppose if you are going to take a cube which has length, breadth, height, because one thing is very important to understand here. Suppose if you take plate length will increase, breadth will increase. I mean, because of absorbing certain amount of heat energy either from some surroundings or from anywhere. Here cube means length will increase, breadth will increase, height also will increase. That is the reason we can say volume increases, right? The expansion in area is called areal expansion. The expansion in volume is called volume expansion, right? This is what in case of areal expansion. Similarly, see how delta L by L is directly proportional to delta T. Similarly, delta A by A is directly proportional to delta T. Middle of that we are getting 2 alpha 1. Usually we are using beta to represent areal expansion, gamma to represent volume expansion. Right. In case of areal expansion beta, you can put 2 alpha 1. In case of gamma, that is what volume expansion, you can put 3 alpha 1. Because length, breadth, height. Here length, breadth, here only length. Delta A by A is equal to alpha 1 into delta T. Delta V by V is equal to 3 alpha 1 into delta T. 3 alpha 1 into delta T, right? Now, see this. I already told you what is alpha. That is, what is coefficient of linear expansion. Alpha is coefficient of linear expansion. Okay. And which is the characteristic. Coefficient of linear expansion is the characteristic of the material of the rod. Characteristic of the material of the rod. For example, the rod is made up of aluminum or copper or brass or iron. And that particular material, it depends upon characteristics of the material of the rod. And you can see this table. In this table we have values of coefficient of linear expansion for some of the materials what we come across in our daily life, mostly aluminum, brass, iron, copper, silver, gold, glass. So glass means especially they have given the value for Pyrex glass. And at last lead. See here, okay. See, it is what 2.5 for aluminum, and it is brass 1.8, and iron it is 1.2, copper 1.7, and silver 1.9, and gold 1.4, glass 0.32, lead 0.29. Okay, lead is 0.29. That is okay. Right now. Similarly, see how we discussed coefficient of linear expansion. Similarly, you can discuss coefficient of volume expansion. That is what alpha V is equal to. Alpha V is equal to delta V by V into 1 by delta T. Delta V by V into 1 by delta T. Okay, that is what coefficient of volume expansion. Alpha V is also a characteristic of a substance, but it is not strictly a constant. It depends in general on temperature. That is what delta T. Okay. When alpha V becomes constant means that you can see through this graph. You can observe here. Alpha V becomes constant. Okay. Only at a high temperature. See here. This is 250 now. It is 500. It is for 10 to the power of minus 5 Kelvin. See here you can see somewhat constant now, that is. Okay. And this expansion also, whatever it may be, see the temperature may be minus 50, maybe 0 degrees centigrade, maybe 50 degrees centigrade, 100 degrees centigrade, 500 degrees centigrade, 1000 degrees centigrade. There is no limit now. See, generally industrial temperature values are high, right? For example, 200 Kelvin, 100 Kelvin, like that. Suppose if we go to that ice continents, for example Australia, in our country Jammu Kashmir, there we have to experience less temperature values like minus 10 degrees centigrade, minus 20 degrees centigrade, like that. Right. Finally, what I am saying is, regarding some materials, the temperature range is 0 degrees centigrade to 100 degrees centigrade, and from this table you can compare the values of coefficient of expansion for different materials. For example, the aluminum has high value 2.5. Next is brass. Next is 1.2. That is iron, like that. Okay. And you can also say that from this table, copper expands about 5 times more than glass for the same rise in temperature. Copper expands nearly 5 times more than the glass for the same rise in temperature. Generally or normally, metals expand more and have relatively high values of alpha. Generally, metals expand more and have relatively high values of alpha 1. High values of alpha 1. Okay, now see this one. This is the graph I already told you. This is temperature versus coefficient of volume expansion. And the important point we have to notice here is when alpha V becomes constant. So generally alpha V becomes constant at high temperature. But in case of alpha 1, that is what coefficient of linear expansion, what we told? We told that it is a characteristic of the material of the rod. But here what we are saying, it depends, basically it is okay, but it is not stricter. See, it also depends upon the temperature here now. So that is what here it will become as temperature independence. That is what at high temperature. At high temperature. See, it is seen that alpha V becomes constant only at a high temperature. Next, we also have some values. We also have some values of coefficient of volume expansion for different materials. For example, if you take aluminum, right? If you take aluminum, it is like 7 into 10 to the power of minus 5. I didn't write on the board because same like coefficient of linear expansion. You just imagine. For brass, alpha V, that is coefficient of volume expansion is 6 into 10 to the power of minus 5. And for iron, it is 3.55 into 10 to the power of minus 5. Paraffin, it is 58.8 into 10 to the power of minus 5. Glass, ordinary glass means 2.5 into 10 to the power of minus 5. And Pyrex glass means 1 into 10 to the power of minus 5. Hard rubber means 2.4 into 10 to the power of minus 4. Inward steel, 2 into 10 to the power of minus 6. Mercury, 18.2 into 10 to the power of minus 5. Water, 20.7 into 10 to the power of minus 5. Alcohol, that is what ethyl alcohol, 110 into 10 to the power of minus 5. All these values are per Kelvin. Okay, right. And the information what we can say regarding the volume expansion is, for some common substances, that is the temperature range is 0 degrees centigrade to 100 degrees centigrade. 100 degrees centigrade. And we can also see thermal expansion of these substances. These substances is rather small with materials like Pyrex glass and inward steel. Just now I told you the values, no? So you just compare all the values, then you can conclude the information what I am saying. And based on the values what I told you, alpha V for alcohol, that is ethyl alcohol, is more than mercury and expands more than mercury for the same rise in temperature. That is the important point we have to keep in mind, because mercury we are utilizing to design or to construct a thermometer. That's why I am asking you to remember, because there is a chance to rise 1 mark bit, either 1 mark MCQ, either for board point of view or NEET point of view. Right, now we are going to discuss about water. See, I already told you in our previous classes, water exhibits a special behavior over rest of the liquids. What is that special behavior means? Most of the liquids are going to expand when they absorb certain amount of heat energy from the surroundings. But in case of water, water is going to contract from 0 to 4 degrees centigrade. After that it is going to expand as usual like rest of the liquids. This behavior is called as anomalous expansion of water. This is the reason, you can see from that is what National Geographic Channel and Discovery Channel, you can see the lakes, especially in winter, the surface of the lake, it's totally become like solid, that is what it is, full of ice. But if you try to dig that ice, inside water is present. Okay, you can see that news, that is what nature related channels, Animal Planet, National Geography, right, Discovery Channel. Some animals, the sea animals like That is what, I don't know the clear names of the animals, but they are going to dig. If they are going to dig, under the ice, fishes are present and water also present. Okay. See, why the surface of the lake becomes totally solid, it is filled with totally ice means, this is the reason. Anomalous expansion of water is the reason. Right. One more example I can say, see, cracks to the walls. Cracks to the walls is also the cause, the reason behind that the cracks is anomalous expansion of water. Here you can see. See, the water contracts on heating between 0 degrees centigrade to 4 degrees centigrade, as I told already. The volume of a given amount of water decreases as it is cooled from room temperature until its temperature reaches 4 degrees centigrade. Below 4 degrees centigrade, the volume increases and therefore the density decreases. Right, here we have to remember one more relation, that is what density is equal to mass by volume. Density is equal to mass by volume. Without changing the mass, if volume is going to increase means density will be decreased. That is what inversely proportional. So based on the information, you can say that water has a maximum density at 4 degrees centigrade. Water has a maximum density at 4 degrees centigrade. This property has an important environmental effect. That is what bodies of water such as lakes and ponds freeze at the top first. As the lake cools towards 4 degrees centigrade, water near the surface loses energy to the atmosphere, becomes denser and sinks. So if it is warmer, certain amount of water that is warmer, less density, water near the bottom rises. However, once the colder water on top reaches the temperature below 4 degrees centigrade, it becomes less dense and remains at the surface. This is the reason it freezes. If water did not have this property, for example, you go for a negative aspect. If water did not have this property, that is what anomalous expansion of water, lakes and ponds would freeze from the bottom up, which would destroy much of their animal and plant life. Okay, from botany and zoology, what are the living beings under the water in lakes and ocean, but mostly I am going to talk about lakes and ponds. See, the living beings which is growing under the lakes in the water, right, among water molecules, what will happen? It will destroy, it will totally destroy. You just imagine one lake totally become as ice. Then what happens to the fishes and the plants which are growing under the water? What happens? So our common sense tells, we need not to go to the subject. Our common sense tells that the total will destroy. Either plants, small plants or fishes or any other will totally die and will totally destroy. So that's why anomalous expansion of water, that is the special behavior of water, which is very important for atmosphere point of view, for environmental point of view. Now, see, regarding the gases, what can we say? At ordinary temperature, till now we talked about solids. That is what coefficient of linear expansion, coefficient of aerial expansion, coefficient of volume expansion. After that, we came to discuss liquids, right? There mostly we concentrated on water. Now we are going to discuss about the gases. So regarding the gases, at ordinary temperatures, expands more than solids and liquids. Generally we can sense in our chemistry lab, in our daily life also you can sense. For liquids, the coefficient of volume expansion is relatively independent of the temperature. But for gases, it is dependent on the temperature. It is dependent on the temperature. It's the most important point, because there is a difference in the behavior of solids when compared, behavior of liquids when compared to the gases. Suppose, for example, if you take an ideal gas, the coefficient of volume expansion at constant pressure can be found from this ideal gas equation, that is PV is equal to nRT. Otherwise, PV is equal to mu RT. P is the pressure, V is the volume, mu is the number of moles of the gas, right? T is the temperature, right? And R is the universal gas constant. That's what we discussed in our previous class. That is 8.31 joule per mole per Kelvin. So here I have written that formula relation, and from this formula you can write P into del V is equal to mu into R into del T at constant pressure. This relation is correct at constant pressure. After that, delta V by V is equal to delta T by T. Delta V by V is equal to delta T by T, that is alpha V is equal to 1 by T. Alpha V is equal to 1 by T for ideal gas. Suppose for example at 0 degrees centigrade, alpha V is 3.7 into 10 to the power of minus 3 per Kelvin, means which is much larger than for solids, and liquids, right? And this equation, whatever the equation we have written, this equation shows that alpha V is equal to 1 by T for gas, shows that temperature dependence of alpha V. See whether the suppose if temperature is going to increase, means this will be decreased, because it is inversely proportional relation. For a gas at room temperature and at constant pressure, alpha V is about 3300 into 10 to the power of minus 6 per Kelvin, as much as order of magnitude larger than the coefficient of volume expansion of typical liquids. And you can see this graph also. That is what here it is, right? This graph is indicating that anomalous expansion of water. And regarding this thermal expansion of water, this is the graph. See here you can see a maximum, which is what, this is the temperature, this is the temperature and this is the density, right? Here you can see maximum density. Now you can also say that there is a simple relation between the coefficient of volume expansion and the coefficient of linear expansion. See, coefficient of volume expansion means three things we have to consider in case of solid matter, that is length, breadth, height. Suppose in case of liquids, means liquids has no definite shape, so shape of the liquid is the shape of the container. And in case of gases also, gases has no free surface also. So in our previous chapter, that is mechanical properties of fluids, we concluded. What about the surface tension? So while discussing about surface tension, we discussed a lot of information about what is meant by free surface and how liquids has free surface when compared to the gases. Okay, now we are going to discuss the relation between coefficient of linear expansion and coefficient of volume expansion. That is what you can write, delta L is equal to alpha 1, see here, delta L is equal to alpha 1 into L into delta T. See, in the chapter of units and measurement, I told you, in the chapter of units and measurement, I told you length, breadth, height, distance, displacement. See, all these five indicates that some of the gap between 2 points, generally, right? Some of the gap between 2 points. So, if you come in that point of view, delta L is equal to alpha 1 into L into delta T. Suppose if you go for delta V, that we have to write L plus delta L whole cubed minus L cubed. That is approximately equal to 3L square delta L. But in this equation, if you see the terms delta L square and delta L cube, actually here delta L square and delta L cube terms also there, which can be neglected. We can neglect these two things if you compare with delta L, because delta L is small compared to L. So that finally you can write delta, after completion of the negligible terms, you can write finally delta V is equal to 3V delta L by L. 3V delta L by L, that is equal to 3V alpha 1 into delta T. See here, see delta L by L means you can write alpha 1 into delta T, no? So 3V into alpha 1 into delta T. So alpha V is equal to 3 alpha 1. Alpha V is equal to 3 alpha 1 is the conclusion finally. What happens by preventing the thermal expansion of a rod? For example, it's okay, it is the relation between coefficient of volume expansion and coefficient of linear expansion. That is what alpha V is equal to 3 alpha 1. Okay, right. Now we are going for general example. Suppose you are taking a rod, that rod is fixed between two ends. See, suppose if you are going to heat this rod, what will happen? How the expansion will be? That is what here you can discuss. Thermal stress. Due to the external forces pivoted by the rod, due to the external forces provided by the rigid support at the ends, stress will be developed. That corresponding stress is called as thermal stress. For example, if you take a rod, if you consider a rod of length 5 meters and area of cross section 40 centimeters square, for expanding while the temperature rises by 10 degrees centigrade, you can say that the coefficient of the linear expansion of steel, because if the rod is steel means the coefficient of linear expansion, that is alpha 1 is 1.2 into 10 to the power of minus 5 per Kelvin. Regarding these dimensions, you can say that the compressive strain, that is delta L by L, will become like 1.2 into 10 to the power of minus 4. And Young's modulus of the steel already we know, that is 2 into 10 to the power of 11. And you can say delta F by A will become 2.4 into 10 to the power of 7. And after that, you can say delta F is equal to, delta F will become approximately equal to, delta F will become approximately equal to 10 to the power of 5 newtons. 10 to the power of 5 newtons. Okay, right. If two such steel rails fixed at their outer ends or in contact at their inner ends, a force of this magnitude can easily bend the rails, right? So that rod is going to bend because of this thermal stress. That is what the corresponding stress developed in the rod because of heating. Okay, right. So it is what somewhat lengthy class. So you please be listen carefully because the matter is very important. That's why I can't stop in the middle of that. Okay, right. So in this class we discussed about thermal expansion in case of solids, in case of liquids, and in case of gases also. Okay, right. So our next class will continue with the next continuation. We have 2 example problems, right? So next class we will continue with the next continuation example problems. Thank you.